Every 17 minutes, 3I Atlas travels the distance from Earth to the Moon. At that speed, it could have bypassed our solar system entirely, continuing its journey through the cosmic deep. Instead, it chose to linger, following the exact plane where our planets orbit, arriving when our most powerful instruments could study it. This isn't how random space debris behaves. Random objects don't announce themselves with internal illumination. They don't time their arrivals for maximum scientific observation. They don't position themselves like subjects posing for a cosmic photograph. Harvard astrophysicist Avi Loeb believes 3I Atlas might be a decoy, a cosmic lure designed to capture our attention while something else unfolds in the shadows. Tonight, we examine the evidence that suggests we're not merely observing 3I Atlas, we're being observed in return. What we discover may transform your understanding of what lies between the stars, because if this visitor was sent deliberately, then the universe is far less empty than we ever imagined. The question might not be whether we're alone, but rather, what does our cosmic visitor want us to see? Now, prepare yourselves. We begin. Part 1. Could 3I Atlas be bait? Sometimes the most obvious explanation is exactly what someone wants you to believe. On July 1st, 2025, astronomers at the Atlas survey in Chile spotted something extraordinary hurtling through our solar system. They called it 3I Atlas, the third confirmed visitor from another star system. But what if this cosmic wanderer isn't what it appears to be? What if it's something far more calculated? Professor Avi Loeb of Harvard University has proposed a provocative possibility. 3I Atlas might be a decoy. Not a natural comet drifting aimlessly through space, but bait, a carefully crafted object designed to attract our attention while something else unfolds elsewhere in the darkness. In this context, a decoy isn't just any misleading object. It's a natural-looking visitor that draws telescopes, resources, and scientific focus to one location while masking activity in another. The timing is particularly intriguing. 3I Atlas reaches its closest approach to the Sun, its perihelion, around October 30th, 2025. During this critical window, when every major observatory on and off Earth will be watching, what opportunities might arise for undetected surveillance? 3I Atlas matters because interstellar visitors are extraordinarily rare. Before this object, we had documented only two others. One Oumuamua in 2017, which sparked debates about artificial origins due to its unusual acceleration, and two Borisov in 2019, which behaved like a textbook comet. The discovery of a third visitor so soon after establishing detection capabilities seems almost convenient. What makes 3I Atlas particularly suspicious to Loeb are several alignment factors. The object travels remarkably close to the ecliptic plane, the same plane where Earth's zodiacal dust and all major planets orbit. This alignment is statistically unlikely for a random interstellar traveler. It's also perfectly positioned for monitoring Earth's neighborhood during its closest solar approach. The Galileo project, Loeb's own scientific initiative dedicated to searching for extraterrestrial technology, has strategically planned observations around this very time frame. NASA's current assessment presents 3I Atlas as exactly what it appears to be, an interstellar comet displaying typical dust coma and tail features, posing no threat to Earth. Their analysis shows a natural object following predictable physics, outgassing materials as it approaches the Sun's warming influence. Yet, underneath this conventional interpretation lies a series of subtle anomalies that refuse to fit neatly into standard cometary models. If hypothetical advanced civilizations wanted to mask their presence or activities in our solar system, why choose this moment? Why use an interstellar comet as camouflage? The answer might lie in the perfect cover such an object provides. Every telescope, every sensor, every monitoring system would naturally focus on this unprecedented visitor. Meanwhile, other activities could proceed unobserved in the shadow of our collective attention. Loeb's speculation extends to what he calls a stealth hybrid asteroid spacecraft concept. a technological object disguised within natural materials, indistinguishable from genuine comets until subjected to extremely close scrutiny. While clearly labeled as speculative, this idea raises profound questions about how we might detect truly sophisticated deception. Several observational signatures could reveal 3I Atlas as more than it seems. Its brightness distribution appears unusually steep, suggesting light dominated by the nucleus rather than surrounding dust, potentially indicating internal illumination. The object's apparent lack of a substantial tail, despite active dust emission, contradicts standard cometary behavior. Its trajectory includes precisely tuned planetary encounters that seem almost choreographed. Each of these anomalies deserves rigorous investigation. The key to testing any decoy hypothesis lies in falsifiability. If 3I Atlas displays mass loss rates, coma profiles, and spectroscopic signatures consistent with known comets, the extraordinary claims weaken considerably. If anomalous behaviors persist under scrutiny, if the object demonstrates characteristics inconsistent with natural processes, then more exotic explanations remain viable. The stakes extend far beyond academic curiosity. What we learn about 3I Atlas could revolutionize our understanding of interstellar materials, cometary evolution, and the prevalence of technological signatures in space. If natural, it provides unprecedented insights into materials formed around distant stars. If artificial, it suggests intelligence sophisticated enough to create nearly perfect mimicry of natural objects. Our timeline for answers is remarkably compressed. 3I Atlas approaches perihelion around October 30th, 2025, offering optimal observing conditions through September. Solar conjunction then renders it unobservable until early December, when it emerges on the opposite side of the Sunday. By March 2026, potential geometric alignments with Jupiter could provide additional observation opportunities if the object survives its solar encounter intact. The beauty of the decoy hypothesis lies in its testability. We don't need to accept extraordinary claims on faith. Instead, we can apply rigorous, transparent evidence standards to evaluate each piece of the puzzle. We can document both mainstream interpretations and heterodox possibilities, letting data guide conclusions rather than preconceptions. Yet we must proceed carefully. The history of astronomy includes numerous cases where unusual observations initially suggested artificial origins, only to reveal exotic but natural phenomena. Pulsars were briefly considered potential alien beacons. Fast radio bursts sparked speculation about extraterrestrial communications. In each case, natural explanations eventually prevailed through patient, methodical investigation. 3I Atlas represents a unique opportunity to practice what we might call dignified skepticism, taking extraordinary claims seriously enough to test them rigorously while maintaining appropriate scientific caution. Whether this visitor proves natural or something more, the process of investigation advances our capabilities for detecting truly anomalous phenomena. As we embark on this investigation, one question echoes through the data. In a universe where deception could theoretically occur at cosmic scales, how would we know if we were being watched? The answer may be hiding in plain sight, disguised as just another comet from the stars. Part 2. Light from Within, Dissecting the Self, Illumination Claim. When light behaves in ways that challenge physics textbooks, astronomers pay attention. Avi Loeb's most provocative claim about 3I Atlas centers on an unusual brightness profile that appears to defy conventional explanation. According to his analysis, the steep 1/r⁴ power brightness distribution surrounding the object suggests something extraordinary. Emission dominated by the nucleus itself, possibly requiring an internal light source rather than simple reflection of sunlight. This assertion strikes at the fundamental question of how 3I Atlas produces the light we observe. Traditional comets shine by reflecting solar radiation and scattering sunlight through clouds of ejected dust and gas. But if Loeb's interpretation proves correct, 3I Atlas might be illuminating itself through some unknown mechanism, a characteristic that would separate it dramatically from any natural comet in our catalogues. The evidence begins with a single, crucial image captured by the Hubble Space Telescope on July 21, 2025. This photograph reveals what astronomers describe as a teardrop cocoon surrounding the object, with a distinct dust plume extending from the sun-facing side. NASA's analysis team, led by Comet expert David Dewitt, interpreted these features as entirely natural, the expected signature of a comet releasing material as solar heating drives sublimation of surface ices. Yet Loeb sees something different in the same data. Where mainstream astronomers observe standard cometary outgassing, he identifies brightness patterns that seem inconsistent with pure reflection and scattering. The mathematical details matter here. Typical cometary comas display brightness that falls off as 1 over r squared with distance from the nucleus, reflecting the natural density distribution of dust particles moving away at steady velocities. 3I Atlas appears to show a steeper falloff, 1 over r to the 4th power, suggesting a more concentrated light source. Why does this mathematical distinction matter? In physics, different power laws reveal different underlying mechanisms. A 1 over r squared profile indicates particles spreading through space under their own momentum, scattering sunlight like tiny mirrors. A 1 over r to the 4th power profile suggests something more concentrated, more focused, potentially a point source of illumination embedded within the nucleus itself. Loeb has considered various natural mechanisms that might produce such internal heating. Frictional interactions with the interstellar medium during the object's long journey could theoretically generate warmth, but his calculations suggest this heating would prove marginal at best. Ram pressure from zodiacal dust in our solar system might compress the object's outer layers, creating friction, but again, the energy budget appears insufficient. The dust lifetimes required for sustained illumination seem to stretch beyond reasonable physical limits. These size implications prove particularly intriguing. If 3I Atlas relies on internal illumination rather than solar reflection, the object could be much smaller than standard analysis suggests, perhaps less than 100 meters in diameter, rather than the kilometer-scale estimates derived from assuming pure reflection. Such a compact size would align more closely with what we might expect from an artificial construction, where efficiency and structural integrity favor smaller, denser designs. Contrast this with the upper limits established by Hubble observations. The telescope's imaging capabilities suggest an effective radius of less than approximately 3 kilometers for any central nucleus, assuming typical cometary albedos around 4%. If internal illumination dominates, these size estimates could shrink by an order of magnitude, placing 3I Atlas in a category more consistent with technological rather than geological scales. Loeb has also explored exotic natural alternatives. Could 3I Atlas be a radioactive fragment from some stellar catastrophe, glowing with the decay heat of unstable isotopes? His estimates suggest even this dramatic scenario fails to provide adequate energy for sustained illumination across the observed timeframes. The half-lives and energy densities required stretch beyond reasonable astrophysical expectations. Meanwhile, mainstream interpretations continue to favor conventional explanations. The Hubble analysis team finds dust loss rates and tail development entirely consistent with comets first detected around 3 to 4 astronomical units from the sunday. Their models require no internal power source to explain the observed brightness, coma structure, or temporal evolution. The teardrop shape emerges naturally from directional dust emission combined with radiation pressure effects. Testing these competing interpretations requires sophisticated observational techniques. Multi-wavelength photometry could reveal color temperatures inconsistent with reflected sunlight. Spectroscopy from the James Webb Space Telescope might detect emission lines characteristic of specific heating mechanisms. Temporal variability studies could identify modulation patterns that distinguish internal sources from reflected illumination. Ground-based observations offer additional diagnostic tools. Polarization measurements could separate reflected light from thermal emission. Phase curve analysis, studying how brightness changes with viewing angle relative to the Sun, might reveal geometry-locked illumination patterns inconsistent with scattering from distributed dust particles. What would definitively favor the decoy hypothesis? Several signatures stand out: narrowband emissions at specific wavelengths that don't correspond to solar reflection, coherent temporal modulation suggesting artificial control systems, polarization characteristics incompatible with dust scattering, or brightness variations independent of the object's phase angle relative to the Sun and Earth. Current peer-reviewed literature maintains that available data support natural cometary activity. The Hubble Space Telescope observations, published in multiple iterations as new data become available, consistently find brightness profiles, dust emission rates, and coma morphology within the range of previously observed comets. Yet the investigation continues, driven by the recognition that extraordinary claims require extraordinary scrutiny. The scientific process demands we separate speculation from established fact. Loeb's internal illumination hypothesis represents exactly the kind of bold thinking that advances our understanding, whether by revealing new physics or by demonstrating the limits of conventional explanations. The beauty lies not in predetermined conclusions but in rigorous testing of provocative ideas. As we await higher resolution spectroscopy and continued photometric monitoring, one question illuminates the path forward. In a universe where stars routinely create objects beyond our imagination, could intelligence do the same? The answer might be glowing softly in the darkness, waiting for us to recognize what we're truly seeing. Part 3. Discovery, Path, and Speed. Why 3I Atlas stands out. Speed tells stories that orbits cannot hide. When Atlas telescopes in Chile first photographed 3I Atlas on July 1, 2025, they captured more than just another dot of light among the stars. They documented the fastest visitor our solar system has ever recorded, an object moving at approximately 137,000 miles per hour, or roughly 61 kilometers per second. This velocity alone places 3I Atlas in a category so extreme that its very existence challenges our assumptions about interstellar travel, but the discovery timeline reveals additional intriguing details. While officially reported on July 1st, pre-discovery images extend back to June 14th, suggesting the object had been present in our sky for at least 2 weeks before astronomers recognized its significance. In those 17 days, how much might we have missed? What opportunities for detailed observations slipped away while 3I Atlas masqueraded as just another faint star? The classification as an interstellar object required careful orbital analysis. Unlike comets born in our solar system's outer reaches, 3I Atlas follows a hyperbolic trajectory, a mathematical signature indicating it remains gravitationally unbound to the Sunday. Its orbital energy exceeds the escape velocity of our solar system by such a margin that no known mechanism could have accelerated it from local origins. This object genuinely comes from somewhere else, carrying velocity acquired across light years of interstellar space. Yet speed represents only the beginning of 3I Atlas's remarkable characteristics. NASA's safety assessment places its closest approach to Earth at approximately 1.6 to 1.8 astronomical units, roughly 240 to 270 million kilometers. While this distance ensures no threat to our planet, it positions the object perfectly for detailed observation during its most active phase. The perihelion timing proves particularly significant. 3I Atlas reaches its closest solar approach around October 30th, 2025, at approximately 1.4 astronomical units, just inside Mars's orbital distance. This timing places peak activity during optimal observing season for Northern Hemisphere telescopes, before winter weather and shorter nights complicate ground-based observations. However, the observability window includes a critical gap. 3I Atlas remains visible to ground-based telescopes through September 2025, offering several months of pre-perihelion monitoring. Then, solar conjunction intervenes. rendering the object unobservable as it passes behind the Sun from Earth's perspective. The comet emerges in early December, potentially transformed by its close solar encounter. The heliocentric geometry adds another layer of intrigue. 3I Atlas approaches from the direction of Sagittarius, traveling nearly parallel to the ecliptic plane, the same plane containing Earth's orbit and the concentrated dust of the zodiacal light. This alignment maximizes the object's interaction with materials already present in our solar system while positioning it for optimal study from Earth-based observatories. Comparing 3I Atlas to its interstellar predecessors reveals both similarities and crucial differences. 1I Oumuamua tumbled through our system in 2017, displaying unusual acceleration that sparked debates about artificial propulsion systems. 2Y Borisov arrived in 2019, behaving like a conventional comet with gas and dust emission clearly visible from great distances. 3I Atlas combines aspects of both, clearly active like Borisov, yet following a trajectory and displaying characteristics that echo the mysteries of Oumuamua. The velocity comparison proves particularly striking. While both previous interstellar visitors moved quickly by solar system standards, 3I Atlas exceeds them substantially. This extreme speed could result from gravitational acceleration by unseen stellar companions, ejection from dense star-forming regions, or encounters with massive objects during its interstellar journey. Each possibility carries implications for understanding the object's origins and composition. Coordinated observations across multiple facilities demonstrate unprecedented international cooperation. The Hubble Space Telescope provides high-resolution imaging capabilities. The James Webb Space Telescope offers infrared spectroscopy to identify chemical composition. The Transiting Exoplanet Survey satellite monitors brightness variations. Swift spacecraft contributes ultraviolet observations. Ground-based facilities like the Keck Observatory and future Vera Rubin Observatory add continuous monitoring capabilities across multiple wavelengths. This multi-facility approach proves crucial because 3I Atlas presents a moving target with limited observation windows. Unlike asteroids or comets that remain visible for years, interstellar objects pass through our system quickly, offering single opportunities for detailed study. Missing key measurements during optimal viewing periods means losing scientific data forever. The path implications for testing any decoy hypothesis prove significant. 3I Atlas's trajectory ensures predictable periods when Earth-based observation becomes difficult or impossible. During solar conjunction, ground-based telescopes cannot monitor the object directly. These blackout periods create natural windows when activities around 3I Atlas might proceed undetected from Earth's perspective. Such observational limitations strengthen the case for space-based assets positioned away from Earth. Spacecraft orbiting other planets or stationed at gravitationally stable Lagrange points could maintain surveillance during Earth's blind periods. The question becomes, do we have such assets positioned appropriately, and if so, are they equipped to monitor unexpected visitors? The orbital mechanics also create opportunities for close-range observation. Mars reaches relatively close proximity to 3I Atlas around October 3, 2025, potentially allowing high-resolution imaging from Mars Reconnaissance Orbiter's HiRISE camera. The geometry of this encounter would provide perspectives impossible from Earth-based observation alone. Looking forward, the March 2026 timeframe offers additional opportunities. If 3I Atlas survives its solar encounter intact, potential geometric alignments with Jupiter could enable observation from different angles, revealing surface features or structural details invisible during the object's initial approach. Yet time remains the ultimate constraint. Unlike local solar system objects that astronomers can study repeatedly over multiple orbits, 3I Atlas offers a single pass through our neighborhood. Every observation must count. Every instrument capability must be maximized. Every international cooperation must be coordinated. As we track this unprecedented visitor across our sky, one realization becomes inescapable. In a universe where objects routinely travel between stars, the most extraordinary aspect of 3I Atlas might not be its speed, but its timing. Sometimes the fastest objects carry the most carefully planned arrivals. Part 4. What the best early paper says on the subject. Science advances through careful observation, not spectacular headlines. The definitive early analysis of 3I Atlas emerged from one of astronomy's most respected research teams. David Jewett of UCLA, working with colleagues and utilizing Hubble Space Telescope observations, published findings that ground our understanding of this interstellar visitor in measurable physical reality rather than speculative possibility. Their paper, updated multiple times as new data became available, presents 3I Atlas as clearly active at a distance of approximately 3.8 astronomical units from the Sun. This activity appears entirely natural, dust particles escaping from the sun-facing side of the nucleus, creating the characteristic coma and faint tail signatures that define active comets throughout our solar system. The quantified dust loss rate provides crucial insight into the object's behavior. According to Jewett's team, 3I Atlas ejects material at approximately 12 times the square root of particle size in micrometers, measured in kilograms per second. For typical dust particles ranging from 1 to 100 micrometers in diameter, this translates to mass loss between 12 and 120 kilograms per second, rates entirely consistent with other comets observed at similar distances from the Sun. These measurements matter because they establish physical constraints on any alternative explanations. The dust production requires specific energy inputs to drive sublimation of surface materials. The particle sizes and velocities follow predictable patterns based on gas, drag, and radiation pressure. The temporal evolution matches expectations for objects heated by increasing solar radiation as they approach perihelion. Nucleus size constraints emerge from careful analysis of brightness and coma structure. Jewett's team determines an effective radius of less than 2.8 kilometers for the central solid body, assuming typical cometary albedo values around 4% reflectivity. This size estimate depends critically on assumptions about surface composition and light scattering properties, but places 3I Atlas in the range of other well-studied comets. If carbon monoxide sublimation drives the observed activity, as suggested by the onset distance and mass loss rates, the nucleus could be even smaller. CO sublimates at lower temperatures than water ice, enabling activity at greater distances from the Sun. This early activation suggests a composition rich in volatile materials that vaporize readily under modest heating. The inner coma surface brightness distribution receives particularly careful analysis in the Jewett paper. By modeling how light scatters from dust particles moving away from the nucleus at different velocities, the team reconstructs both particle size distributions and ejection speed profiles. Their results indicate typical cometary behavior: larger particles moving slowly, smaller particles accelerated to higher velocities by gas drag from sublimating ices. These brightness profile fits address directly the alternative interpretations proposed by R.V. Loeb. Where Loeb suggests internal illumination to explain steep brightness gradients, Jewett's team finds standard cometary dust scattering sufficient to match observations. The mathematical models reveal no need for exotic energy sources beyond solar heating of surface materials. The NASA press analysis aligns closely with peer-reviewed findings. The dust plume extending from the sun-facing hemisphere, the faint tail signatures pointing away from the sun, and the overall teardrop cocoon structure all match expectations for natural cometary activity. The object behaves exactly as physics predicts for a comet approaching the Sun for the first time in its existence, yet tensions remain between mainstream interpretations and alternative analyses. The precise power law describing brightness falloff with distance from the nucleus continues to generate debate. Loeb's assertion of 1 over r to the 4th power profiles contrasts with Jewett's finding of more conventional gradients. Resolution requires additional high-resolution observations with improved signal-to-noise ratios. The Hubble observations enable specific predictions for continued monitoring that extend far beyond simple brightness measurements. Color measurements should remain consistent with reflected sunlight modified by dust scattering properties, following well-established relationships between particle size distributions and wavelength-dependent scattering efficiency. Mass loss rates should evolve predictably as solar heating increases toward perihelion, matching theoretical models of how volatile materials sublimate under increasing thermal stress. Gas species should appear in spectroscopy at wavelengths corresponding to known molecular transitions, particularly the distinctive fingerprints of water vapor at 1.6 micrometers, carbon monoxide near 2.3 micrometers, and carbon dioxide around 4.3 micrometers. These spectroscopic signatures provide direct chemical evidence that no amount of brightness analysis or morphological study can replace. The instrumentation required for these follow-up observations represents the cutting edge of astronomical technology. The James Webb Space Telescope's unprecedented infrared sensitivity could detect trace amounts of exotic molecules that might indicate unusual formation environments or subsequent processing. Ground-based facilities like the Very Large Telescope's high-resolution spectrographs offer complementary capabilities across different wavelength ranges, while adaptive optics systems compensate for atmospheric turbulence to achieve near space-based image quality. Radio astronomy adds another dimension to the observational campaign. Facilities like the Atacama Large Millimeter Array could detect molecular emission lines from carbon monoxide, hydrogen cyanide, or other species that sublimate from the nucleus and fluoresce under solar ultraviolet radiation. These observations would provide independent confirmation of chemical composition while potentially revealing species invisible to optical and infrared techniques. Follow-up observational proposals focus on spectroscopic detection of specific gas species, but they also encompass broader questions about 3I Atlas's place in the taxonomy of interstellar objects. Carbon monoxide, carbon dioxide, and water vapor each produce characteristic absorption or emission features that reveal not only their presence but also their physical conditions, temperature, density, velocity distributions, and excitation states that trace the energy balance within the expanding coma. The isotopic composition measurements represent perhaps the most definitive test of 3I Atlas's origins. Different stellar environments produce characteristic isotope ratios that serve as fingerprints of formation conditions. The ratio of carbon-12 to carbon-13, oxygen-16 to oxygen-18, or nitrogen-14 to nitrogen-15 could reveal whether 3I Atlas formed in a stellar system similar to our own or in more exotic environments around different types of stars. Comparing 3I Atlas to the detailed chemical analysis of 2-1 Borisov could reveal whether interstellar comets share common formation environments or display systematic differences that reflect the diversity of planetary systems throughout the galaxy. 2I Borisov showed unusually high carbon monoxide abundance compared to solar system comets, suggesting formation in colder, more distant regions around its parent star. If 3I Atlas displays similar chemical signatures, it might indicate common formation mechanisms for interstellar comets. If it shows different composition, the diversity would suggest that interstellar space contains representatives from many different types of stellar environments. The temporal evolution of spectroscopic features provides dynamic information impossible to obtain from single observations. As 3I Atlas approaches the Sun, different volatile materials should begin sublimating at predictable distances based on their vapor pressures and thermal properties. Water ice becomes active around 3 astronomical units, carbon dioxide around 5 to 7 astronomical units, and carbon monoxide at even greater distances. This sequence of activation should appear in spectroscopic monitoring as new emission lines emerge and strengthen according to well-understood physical relationships. Dust composition analysis through spectroscopic techniques could reveal the silicate mineralogy, organic compound abundances, and refractory element ratios that characterize the solid materials embedded within 3I Atlas. These measurements would address fundamental questions about dust grain formation around other stars and how interstellar processing might modify original compositions during million-year journeys through space. These peer-reviewed constraints significantly narrow the parameter space available for exotic explanations. If the nucleus measures less than several kilometers in radius and displays coma physics consistent with textbook examples, the burden of proof shifts dramatically toward detecting uniquely technological signatures rather than arguing from ambiguous natural phenomena. However, the constraints also establish clear criteria for what would constitute genuinely anomalous behavior, deserving more exotic interpretation. The document's evolution through multiple RCIV versions illustrates the scientific process in real time with unprecedented transparency. Version 1 established basic observational facts from initial Hubble imaging, providing the first quantitative constraints on nucleus size and activity levels. Version 2 refined mass loss calculations as improved photometric calibration became available. Version 3 incorporated improved astrometry that sharpened orbital element determination and refined predictions for future observation opportunities. Version 4 added spectroscopic constraints as the first chemical measurements became available from ground-based observations. Each iteration demonstrates how careful analysis refines understanding while maintaining core conclusions about natural cometary activity. The iterative process also reveals which aspects of the analysis prove most robust against improved observations versus which elements require revision as new data challenge initial assumptions. This transparency provides valuable insights into how scientific understanding develops in real time rather than through the sanitized narrative that appears in final publications. The version control system used in modern astronomical research enables detailed tracking of how interpretations evolve as evidence accumulates. Future historians of science will have unprecedented access to the complete decision-making process, including false starts, abandoned hypotheses, and methodological refinements that don't appear in traditional publication formats. This progression matters for public communication about fast-evolving astronomical discoveries because it illustrates the difference between preliminary findings and established conclusions. Early reports often contain provisional estimates later refined by improved observations, creating potential confusion when headlines claiming largest or brightest interstellar visitor require continuous updating as measurement precision improves. The scientific process rewards patience and skepticism over premature certainty, but public communication often demands immediate answers to questions that require extended investigation. The challenge for science communicators lies in conveying both the excitement of discovery and the uncertainty inherent in early-stage research. 3I Atlas represents a genuinely significant astronomical event regardless of whether specific preliminary interpretations prove correct. The process of investigation advances scientific capabilities even when individual hypotheses require revision or abandonment. Jewett's team maintains appropriate scientific caution throughout their analysis, acknowledging uncertainties in size estimates, composition inferences, and long-term evolution predictions. They identify specific observations needed to test their interpretations while avoiding claims beyond what current data can support. This conservative approach contrasts with more speculative interpretations that extrapolate beyond observational constraints. But it provides a solid foundation for subsequent research that builds on reliable results rather than provisional speculation. The acknowledgement of uncertainty extends to explicit discussion of systematic errors, calibration uncertainties, and model assumptions that could affect conclusions. Such transparency enables other researchers to evaluate the reliability of different aspects of the analysis while identifying areas where improved observations or alternative approaches might advance understanding. The implications for the DECOY hypothesis prove significant but complex. If 3I Atlas displays radius, mass loss, and coma structure within the range of previously studied comets, claims of artificial origin face substantial evidential challenges. Natural explanations become not just possible but probable, shifting the extraordinary evidence requirement to demonstrably non-natural signatures that cannot be explained through conventional cometary physics. However, the threshold for what constitutes within the range of natural behavior requires careful definition. Comets display enormous diversity in size, composition, activity levels, and structural characteristics. The challenge lies in distinguishing between unusual but natural variations versus genuinely anomalous signatures that demand exotic explanations. Yet the investigation continues, driven by recognition that extraordinary claims deserve thorough testing regardless of prior expectations about probable outcomes. The beauty of the scientific method lies not in predetermined outcomes but in rigorous application of evidence-based reasoning to bold hypotheses. Even hypotheses that ultimately prove incorrect contribute valuable insights by constraining possible explanations and refining investigative methodologies. The peer review process serves as quality control that prevents premature conclusions while ensuring that bold ideas receive fair evaluation based on evidence rather than conventional wisdom. This balance between skepticism and openness to new possibilities represents one of science's greatest strengths in distinguishing reliable knowledge from speculation or wishful thinking. As we await continued spectroscopic observations and approach the critical perihelion timeframe, one principle guides our evaluation. In science, the most elegant explanation often proves correct, but nature occasionally surprises us with complexity beyond our current imagination. The history of astronomy includes numerous examples where unusual observations initially defied explanation, only to reveal new physical phenomena that expanded our understanding of how the universe works. The question remains whether 3I Atlas represents elegant simplicity that confirms our understanding of interstellar objects, or extraordinary complexity that will challenge us to develop new theoretical frameworks for interpreting cosmic phenomena. Part 5. Size, brightness, and oldest comet, competing estimates. Numbers tell different stories depending on who's counting. Early press coverage of 3I Atlas included dramatic claims about its significance, potentially the largest, brightest, or oldest interstellar visitor yet discovered. These superlatives captured public attention and generated scientific interest, but they also illustrate how provisional measurements can create lasting impressions that subsequent analysis must carefully correct. The largest claim emerged from initial brightness observations combined with assumptions about typical cometary composition. If 3I Atlas reflected sunlight like most comets, with albedo values around 4%, its apparent magnitude suggested a substantial solid nucleus. Early estimates reached toward the upper end of comet-sized distributions, potentially exceeding the dimensions of well-studied objects like Comet Hale-Bopp or Comet Hyakutake. However, Hubble Space Telescope observations quickly refined these estimates downward. NASA's official reports cite an upper limit of 5.6 kilometers for the nucleus diameter, while detailed analysis in the Jewett paper suggests an effective radius below 2.8 kilometers. This factor of 2 difference reflects uncertainties in albedo assumptions and the challenge of separating nucleus brightness from surrounding coma contributions. The Vera Rubin Observatory's contribution to size estimation demonstrates how improved observational capabilities continuously refine our understanding. As additional photometric data become available, early size estimates have dropped consistently, suggesting 3I Atlas falls within the normal range of cometary nuclei rather than representing an exceptional giant. The brightest designation requires even more careful qualification. Apparent brightness as seen from Earth depends not only on object size but also on distance, phase angle, and scattering properties. 3I Atlas benefits from a relatively close approach to Earth combined with high activity levels that enhance its visibility. However, intrinsic brightness, corrected for distance and geometric factors, may prove less exceptional than initial observations suggested. Forward scattering effects complicate brightness interpretation significantly. When observing comets at small phase angles, where Earth, the comet, and Sun form acute triangles, dust particles scatter sunlight preferentially toward Earth, creating artificially enhanced brightness. This geometric enhancement can exaggerate apparent luminosity without requiring internal light sources or unusual composition. The oldest comet characterization enters even more speculative territory. Age estimates for 3I Atlas depend on theoretical models of its formation environment and subsequent galactic evolution. If the object originated in older stellar populations or spent extended time in interstellar space, it might preserve materials from earlier epochs of cosmic history. However, determining dynamical age requires detailed knowledge of galactic motion and stellar encounter rates that remain highly uncertain. Photometry alone cannot resolve these competing interpretations reliably. The fundamental challenge involves separating reflected light from the nucleus versus scattered light from surrounding dust particles. Point spread function effects blur this distinction for ground-based observations, while even Hubble's resolution cannot completely isolate nucleus contributions at 3I Atlas's distance. Spectroscopy offers the most promising pathway for resolving size and composition ambiguities. Gas emission lines provide direct chemical fingerprints that reveal sublimating materials and their abundances. Dust color measurements constrain particle composition and size distributions. Thermal infrared observations could detect heat emission from the nucleus surface, enabling independent size estimates based on temperature rather than reflected light. The implications for decoy hypothesis testing prove significant. If 3I Atlas measures small but appears bright due to concentrated central illumination, this supports arguments for internal energy sources potentially inconsistent with natural processes. Conversely, if the object displays typical size-to-brightness ratios with standard coma scattering, natural explanations become more compelling. A useful visualization might track how size and brightness estimates have evolved over time as different instruments contributed observations. Early Atlas survey data provided initial detection and rough brightness. Hubble imaging refined size constraints and revealed coma structure. Ground-based spectroscopy added chemical information. Future James Webb Space Telescope observations will contribute infrared capabilities for thermal measurements. This temporal evolution of measurements illustrates how scientific understanding develops through iterative refinement rather than instant revelation. Early dramatic claims give way to careful analysis that produces more modest but more reliable conclusions. The process requires patience and willingness to revise preliminary interpretations as evidence accumulates. Color measurements deserve particular attention because they constrain both composition and scattering mechanisms. Natural comets display relatively neutral colors reflecting a mixture of rocky and icy materials. Significant color variations might suggest unusual composition or artificial materials designed to mimic natural appearance while serving technological functions. Variability studies add another diagnostic tool. Natural comets often display brightness variations due to irregular nucleus shape, non-uniform surface activity, or rotational modulation. Artificial objects might show different variability patterns reflecting structural design rather than gravitational shaping and impact history. The dust-to-gas ratio provides additional compositional constraints. Typical comets release gas and dust in relatively predictable proportions, reflecting their formation in the outer solar nebula. Unusual ratios might indicate formation in different environments or subsequent processing that altered the original composition. Nucleus density estimates, if achievable, could distinguish between loose aggregate structures, typical of natural comets, versus more coherent constructions that might suggest artificial origin. However, determining density requires both mass and volume measurements that prove extremely challenging for objects observed only briefly at interstellar distances. Current evidence continues to favor natural explanations, but the investigation proceeds with appropriate scientific rigor. Each measurement campaign adds constraints that gradually narrow the range of viable interpretations. The question becomes whether accumulating data will converge on conventional cometary physics or reveal signatures inconsistent with natural processes. As we await continued observations through the critical perihelion period, the size and brightness puzzle reminds us that in astronomy, the most important measurements often prove to be the ones we haven't made yet. Sometimes the smallest objects cast the longest shadows of uncertainty. Part 6. The ecliptic coincidence, clever design or just statistics. In a universe of random trajectories, perfect alignments demand explanation. Avi Loeb's analysis of 3I Atlas includes a statistical argument that cannot be dismissed casually. The object's trajectory aligns remarkably closely with the ecliptic plane, where Earth and other planets orbit the Sunday. According to his calculations, such alignment occurs in only about 0.2% of random interstellar trajectories. When combined with close passages to Mars, Venus, and Jupiter, the probability drops to approximately 0.005%. Odds so low, they suggest deliberate planning rather than cosmic coincidence. But statistics can mislead as easily as they illuminate, and extraordinary claims require careful examination of underlying assumptions. The ecliptic alignment argument centers on a fundamental question about detection bias. Astronomical surveys like ATLAS, which discovered 3I Atlas, concentrate their observing time in regions where they expect to find objects. For surveys designed to detect near-Earth asteroids and comets, this means focusing on the ecliptic plane where most solar system objects reside. This creates what statisticians call a selection effect. We're more likely to discover objects traveling near the ecliptic simply because we spend more time looking there. The question becomes whether 3I Atlas's alignment reflects genuine astronomical rarity or inevitable observational bias. Survey footprint analysis could resolve this ambiguity through careful modeling. By simulating thousands of synthetic interstellar objects with random trajectories and processing them through realistic survey detection algorithms, astronomers could determine what fraction of discoveries would naturally fall near the ecliptic plane. If the simulation matches observed statistics, selection bias explains the alignment. If not, genuine astronomical processes might favor ecliptic trajectories. The planetary flyby language requires particularly careful interpretation. When Loeb describes close passages to Mars at approximately 29 million kilometers, the scale requires context. This distance equals roughly 75 times the separation between Earth and Moon, close by interplanetary standards, but still representing enormous empty space. The object passes near planetary orbits without actually encountering the planets themselves. These geometric relationships do create opportunities for observation by spacecraft orbiting other planets. Mars Reconnaissance Orbiter's high-rise camera could potentially image 3I Atlas during the October 3rd closest approach, providing resolution impossible from Earth-based telescopes. Similarly, the Juno spacecraft at Jupiter might offer unique viewing geometry during later phases of the object's trajectory. However, such observational opportunities exist for any object passing through the inner solar system, regardless of origin. The key question becomes whether 3I Atlas's specific trajectory maximizes these opportunities beyond what random chance might provide. Comparing 3I Atlas to its interstellar predecessors offers additional context. 1I Oumuamua approached from a different direction entirely, passing through the solar system at a steep angle to the ecliptic. 2I Borisov arrived from yet another trajectory, though also remaining relatively close to the plane of planetary orbits. This small sample size prevents definitive statistical conclusions about whether interstellar objects favor particular orientations. Heliocentric longitude and latitude plots could visualize whether 3I Atlas's motion appears unusual compared to known interstellar visitors. Such plots would display the object's position relative to the Sun in coordinates analogous to latitude and longitude on Earth, making trajectory differences immediately apparent to viewers. galactic motion considerations complicate the statistical analysis further. Our solar system moves through the Milky Way galaxy at approximately 220 kilometers per second, following a complex orbit around the galactic center. This motion means that interstellar objects approaching from certain directions will naturally appear aligned with our orbital plane due to geometric projection effects. The timing coincidence with Galileo project observations adds another layer of intrigue to the alignment argument. If 3I Atlas represents a natural object, its perihelion timing during optimal observing season constitutes remarkable luck for astronomers hoping to study interstellar visitors. If artificial, such timing might reflect careful planning to maximize observation opportunities while maintaining plausible natural appearance. Detection technology evolution affects these probabilities significantly. The Atlas survey that discovered 3I Atlas represents recent advancement in astronomical monitoring capabilities. Earlier surveys might have missed similar objects due to sensitivity limitations or observing strategies. As detection capabilities improve, the rate of interstellar object discoveries will likely increase, providing better statistics for evaluating trajectory distributions. Atmospheric and weather patterns introduce additional selection effects. Ground-based surveys observe preferentially during clear nights with good atmospheric conditions. Seasonal variations affect observing time available at different sky positions. These factors could bias discoveries toward objects visible during optimal weather periods or from observatories in specific geographic locations. The anthropic principle provides yet another perspective on apparent coincidences. Observers naturally find themselves in situations where observation is possible. If 3I Atlas arrived along a trajectory that prevented effective study, we might not recognize its significance or artificial nature. Observable alignments might represent the subset of events capable of generating the evidence needed for investigation. Testing the coincidence hypothesis requires expanding beyond single-object analysis to broader population studies. As the Vera Rubin Observatory becomes fully operational, it will discover numerous additional interstellar objects, providing statistical samples large enough to evaluate trajectory distributions quantitatively. If most interstellar visitors align with the ecliptic, the phenomenon proves common rather than exceptional. If 3I Atlas represents a genuine outlier, its alignment gains significance. Survey simulation software could model detection probabilities across different sky positions, accounting for telescope pointing strategies, weather patterns, and observing time allocation. Such modeling would quantify how selection effects influence the apparent distribution of interstellar object trajectories. The ultimate resolution depends on accumulating sufficient data to distinguish between competing explanations. If survey bias explains ecliptic alignment, the DECOY hypothesis loses a significant supporting argument. If the alignment proves genuinely anomalous even after correcting for selection effects, it strengthens claims for deliberate targeting of our solar system neighborhood. As we continue tracking 3I Atlas through its carefully choreographed dance among the planets, one question echoes through the statistical uncertainty. In a universe where coincidences occur routinely, how do we recognize the ones that aren't coincidental? Sometimes the most suspicious thing about perfect timing is its perfection. Part 7. Dust, Gas, and Ram Pressure, the Zodiacal Medium Model. Physics provides elegant explanations when we know where to look for them. R.V. Loeb's analysis of 3I Atlas includes a sophisticated physical model that could explain some of the object's more puzzling characteristics through entirely natural processes. His ram pressure confinement scenario suggests that dust flowing from the comet's surface encounters resistance from zodiacal medium, the sparse cloud of particles that fills the space between planets, creating a confined dust envelope rather than the extended tail typical of most comets. The mathematics behind this model proves surprisingly elegant. According to Loeb's calculations, dust particles ejected from 3I Atlas at typical speeds encounter enough resistance from zodiacal material to halt their outward motion at distances around 3,000 kilometers from the nucleus. This confinement effect would create a compact dust cloud, rather than the streaming tail that extends millions of kilometers behind most active comets. The mass loss rate required for this scenario aligns reasonably well with observations. Loeb estimates approximately 10 kilograms per second of material ejection, falling within the range of 12 to 120 kilograms per second, derived from Hubble Space Telescope analysis by David Jewett's team. While not perfect agreement, the overlap suggests ram pressure effects could contribute significantly to 3I Atlas's unusual appearance. What makes this model particularly intriguing is its independence from nucleus size. Traditional cometry models link mass loss rates directly to surface area available for sublimation, meaning larger nuclei typically produce more dust and gas. The ram pressure scenario depends more on the interaction between ejected material and ambient medium, potentially allowing smaller objects to appear more active than their size would normally suggest. Rotational dynamics add complexity to dust ejection patterns. Early analysis suggests 3I Atlas rotates with a period around 16 hours, creating systematic variations in surface heating and material emission. Surface ejection velocities must exceed approximately 1 meter per second to escape the object's weak gravity, while micron-sized dust particles require speeds around 20 meters per second to overcome radiation pressure effects that might push them back toward the nucleus. These velocity requirements interact with the zodiacal medium in ways that could produce the subdued tail characteristics observed in Hubble images. If ram pressure halts dust expansion within several thousand kilometers, the result would be a compact coma with only faint tail signatures, exactly what astronomers observe when they study 3I Atlas through Earth-based telescopes. The model makes specific predictions about observational signatures that could test its validity. Coma truncation scales should vary with heliocentric distance as the density of zodiacal material changes. Color gradients within the coma might reveal particle size sorting as different-sized dust grains respond differently to ram pressure effects. Polarization measurements could distinguish between dust particles moving freely through space versus those confined by medium interactions. Phase angle dependence offers another diagnostic tool. If ram pressure creates artificial confinement, the coma's appearance should change systematically as Earth's viewing angle relative to the Sun and comet changes. Free streaming dust produces different scattering patterns than confined particle clouds, enabling observations to distinguish between competing physical models. The observational campaign needed to test ram pressure confinement requires coordination across multiple facilities with different capabilities. Hubble Space Telescope provides high spatial resolution imaging to map coma structure in detail. The James Webb Space Telescope contributes infrared spectroscopy that could detect gas species and thermal emission from dust particles. ALMA and NOMA radio telescopes offer unprecedented sensitivity to molecular emission lines that trace gas production rates. Ground-based observatories add continuous monitoring capabilities across multiple wavelengths. Large telescopes like the Keck Observatory or the Future Extremely Large Telescope could track coma evolution with sufficient time resolution to detect systematic changes as 3I Atlas approaches the Sun and encounters varying zodiacal medium density. If observational data match ram pressure predictions for coma truncation, particle size distributions, and temporal evolution, the natural explanation for 3I Atlas's unusual appearance strengthens considerably. The object would represent an interesting example of environmental effects shaping cometary behavior rather than evidence for exotic composition or artificial origin. Conversely, if observations fail to match ram pressure expectations, alternative explanations regain viability. Internal heating sources, unusual composition, or technological signatures would become more plausible if standard environmental effects cannot account for the observed characteristics. The distinction between back-of-envelope calculations and peer-reviewed modeling deserves emphasis throughout this analysis. Loeb's Medium posts provide valuable scientific speculation that advances thinking about 3I Atlas, but they represent preliminary analysis rather than definitive conclusions. The scientific process benefits from bold hypotheses tested against rigorous observational standards. Zodiacal medium properties themselves remain somewhat uncertain, adding complexity to RAM pressure calculations. Particle densities, size distributions, and spatial variations near the ecliptic plane affect how strongly the medium can confine cometary dust. Better characterization of the interplanetary environment would improve predictions for how 3I Atlas should behave if RAM pressure dominates its coma dynamics. The ecliptic plane passage becomes particularly relevant in this context. If 3I Atlas travels through regions with enhanced zodiacal dust density, RAM pressure effects would be maximized, potentially creating the compact coma and subdued tail that distinguish this object from typical comets observed at similar distances from the Sunday. Temperature gradients within the confined coma could produce additional observable signatures. If dust particles remain close to the nucleus longer than in freely expanding comae, they might reach higher temperatures before escaping, creating distinctive thermal emission signatures in infrared wavelengths. Magnetic field interactions represent another potential diagnostic. The solar wind carries embedded magnetic fields that interact differently with confined versus freely streaming cometary material. Spacecraft measurements of magnetic field perturbations around 3I Atlas could test whether its coma behaves like typical comets or displays signatures consistent with RAM pressure confinement. As we prepare for the critical perihelion period when 3I Atlas reaches closest approach to the Sun, the RAM pressure model provides testable predictions for how the object should behave. Enhanced solar heating should increase gas and dust production rates, but if zodiacal medium interactions dominate, the coma might remain more compact than typical comets would display at similar distances. The beauty of this physical model lies in its falsifiability. Clear observational signatures distinguish between RAM pressure confinement and alternative explanations, enabling data to guide conclusions rather than preconceptions. Whether 3I Atlas represents sophisticated environmental physics or something more exotic, the investigation advances our understanding of how objects behave in the complex environment between planets. Part 8. Intercept Ideas, Juno, HiRISE, and Rapid Response Missions. Sometimes the most audacious plans reveal the most practical truths. In the realm of space exploration, opportunity and impossibility often separate by mere kilometers per second of velocity change. When Avi Loeb, working with colleagues Steve Hibbard and John Crowell, proposed retargeting NASA's Juno spacecraft to intercept 3I Atlas, they weren't just suggesting a mission modification. They were illustrating how quickly astronomical discovery can outpace our ability to respond with appropriately positioned assets. The Juno proposal represents both ambitious engineering and sobering reality. Currently orbiting Jupiter and conducting detailed studies of the gas giant's interior structure, Juno possesses sufficient propulsion capability to execute what mission planners call a Jupiter-Oberth maneuver. Using the planet's gravity to amplify engine thrust and achieve the velocity changes needed to reach 3I Atlas by March 2026. The mathematical elegance of such trajectory planning cannot obscure its practical challenges. Juno's propellant margins were designed for Jupiter orbital operations, not interplanetary intercept missions. The spacecraft's aging systems have operated far beyond original specifications, raising questions about reliability during extended operations. Most critically, NASA has made no official announcements regarding such mission retargeting, and community skepticism remains substantial. Yet the scientific payoff of close-range observations would prove extraordinary. Juno carries instruments capable of measuring thermal emission, magnetic field perturbations, dust composition, and plasma interactions around 3I Atlas. At encounter distances potentially measured in hundreds rather than millions of kilometers, such observations could definitively resolve questions about the object's nature that remain ambiguous in Earth-based telescopic data. The Mars Reconnaissance Orbiter's high-rise camera presents a more immediately feasible opportunity. During 3I Atlas's closest approach to Mars around October 3, 2025, geometric alignment could enable high-resolution imaging impossible from Earth-based observation. HiRISE routinely achieves sub-meter resolution of Martian surface features, potentially revealing structural details of 3I Atlas invisible to terrestrial telescopes. However, solar elongation constraints complicate even this relatively straightforward observation. As 3I Atlas approaches the Sun, its position in Earth's sky moves closer to solar glare, creating observational difficulties for both ground-based telescopes and spacecraft oriented toward Earth. The timing of Mars' proximity unfortunately coincides with challenging viewing geometry that may limit observation quality. These coordination challenges highlight broader issues in astronomical rapid response capabilities. Unlike predictions of eclipses or planetary alignments that allow years of advanced planning, interstellar visitor discoveries provide weeks or months of lead time for organizing comprehensive observation campaigns. Existing spacecraft follow predetermined orbits optimized for their primary missions, not opportunistic targets that appear with little warning. The European Space Agency's Comet interceptor mission, currently under development, represents exactly the kind of rapid response capability that 3I Atlas demonstrates we need. Designed to wait at gravitationally stable Lagrange points until suitable targets appear, such missions could respond to interstellar visitors with dedicated instrumentation rather than retrofitted capabilities from missions designed for other purposes. Future interceptor concepts might incorporate modular instrument packages that could be rapidly assembled and launched toward high-priority targets. Solar sail propulsion or ion engines could provide the continuous low-thrust acceleration needed to match trajectories with fast-moving interstellar objects, overcoming the velocity limitations that constrain conventional chemical propulsion systems. The multi-asset coordination required for 3I Atlas observations illustrates both international cooperation potential and operational complexity. Hubble Space Telescope provides optical imaging. James Webb Space Telescope contributes infrared spectroscopy. Ground-based observatories offer continuous monitoring, and potential spacecraft encounters add close-range measurements. Coordinating these diverse capabilities requires unprecedented planning and communication. What would a dedicated flyby mission measure that remote observations cannot? Nucleus thermal mapping could reveal temperature distributions that distinguish between internal heating and solar warming. High-resolution spectroscopy might detect trace gases or unusual isotopic ratios invisible in Earth-based observations. Dust composition analysis could identify materials inconsistent with natural comet formation. Radio observations might detect artificial signals or electromagnetic signatures indicative of technological origin. The policy implications extend beyond individual missions to broader space program priorities. How should space agencies balance ongoing committed operations against opportunities for breakthrough discoveries? What level of mission risk is acceptable when pursuing potentially paradigm-shifting observations? How can international partnerships enable rapid response capabilities that exceed what individual nations could achieve independently? The lead times for spacecraft retargeting reveal fundamental constraints on our current space infrastructure. Major trajectory changes require months of planning, trajectory analysis, and system verification. Propellant budgets limit available velocity changes. Communication delays complicate real-time operations as distances increase. These factors mean that even perfect advance warning might not enable optimal observation strategies. The cost-benefit analysis for intercept missions involves more than immediate scientific return. Demonstrating rapid response capabilities advances preparation for future interstellar visitors, asteroid impact mitigation, and other time-critical space operations. The experience gained in coordinating multi-asset observation campaigns proves valuable for numerous astronomical research programs. Engineering constraints deserve honest acknowledgement alongside scientific enthusiasm. Juno's propulsion system, designed for Jupiter orbital insertion and periodic orbit adjustments, may lack the performance margins required for interplanetary escape trajectories. Component aging affects reliability calculations for extended operations. Power system limitations constrain instrument operation durations at increased distances from the Sunday. Yet the fundamental question remains: what opportunities are we missing by lacking dedicated rapid response capabilities? Every interstellar visitor since 1I Oumuamua has departed our solar system carrying unanswered questions that close-range observations might have resolved. 3I Atlas offers another chance to demonstrate either our observational capabilities or their limitations. The animated trajectory visualizations from the Juno proposal, pork chop plots showing launch windows and arrival opportunities, illustrate the mathematical precision required for interplanetary navigation. These plots reveal how narrow the windows become for intercept missions, emphasizing why rapid decision-making proves so critical in utilizing unexpected opportunities. As we approach 3I Atlas's perihelion, the mission proposals serve dual purposes, highlighting immediate observational possibilities while illustrating broader needs for future interstellar visitor encounters. Whether current spacecraft execute successful observations or reveal the limitations of retrofitted capabilities, the lessons learned will inform planning for the next cosmic visitor that appears without warning. The next interstellar object might arrive with perfect timing for interception, or it might challenge us again to work within the constraints of missions designed for other purposes. Part 9. Comparing the three interstellar visitors, 1I, 2I, 3I. Each visitor writes its own chapter in the encyclopedia of the impossible. The story of interstellar objects in our solar system begins with a mystery, continues through confirmation, and now approaches a new enigma that challenges everything we thought we understood about cosmic wanderers. 1I Oumuamua arrived first, in October 2017, tumbling through our solar system like a cosmic messenger bearing encrypted information we still struggle to decode. Its elongated shape, perhaps 10 times longer than wide, defied expectations about natural object formation. More puzzling still, Oumuamua displayed non-gravitational acceleration as it departed, gaining speed in ways that suggested propulsion without any detectable exhaust or outgassing that typically drives such behavior in comets. The absence of a visible coma or tail around Oumuamua sparked intense debate about its composition and origin. Natural explanations ranged from exotic ice compositions that sublimate without producing visible dust, to solid nitrogen fragments ejected from Pluto-like worlds around distant stars. More provocative interpretations suggested artificial origins, perhaps a discarded technology or even an active probe exploring our solar system. 2I Borisov provided reassuring normalcy when it appeared in August 2019. This object behaved exactly like astronomers expected interstellar comets to behave, displaying a prominent coma and tail visible from great distances, releasing gas and dust at rates consistent with water-ice sublimation, and following predictable physics throughout its solar system passage. Detailed spectroscopic analysis revealed unusual carbon monoxide abundance, suggesting formation in a stellar environment different from our own Sun's protoplanetary disk. Borisov's nucleus measured approximately 1 kilometer in diameter, firmly in the range of natural cometary objects. Its activity began at distances exceeding 3 astronomical units from the Sun, indicating volatile rich composition typical of comets formed in outer planetary regions. The object provided our first detailed chemical analysis of materials formed around another star, revealing both similarities to and differences from solar system comets. 3I Atlas combines aspects of both predecessors while introducing new puzzles that resist easy categorization. Like Borisov, it displays clear cometary activity with visible dust coma and plausible tail signatures. Like Oumuamua, it travels at exceptional speed and follows a trajectory that seems almost precisely engineered for optimal observation opportunities. The combination creates an object that fits no existing category completely, the speed comparison proves particularly striking. While all three objects move rapidly by solar system standards, 3I Atlas exceeds its predecessors substantially, reaching velocities that suggest ejection from dense stellar environments or acceleration by encounters with massive gravitational sources during its interstellar journey. This extreme velocity could result from natural processes, but it also enables rapid transit between star systems that might interest technological civilizations. Chemical and photometric expectations for 3I Atlas remain largely unfulfilled as we await detailed spectroscopic observations. If the object resembles 2Y Borisov chemically, it would support natural formation in protoplanetary disks around other stars. If it displays unusual isotopic ratios, elemental abundances, or molecular species, it might indicate formation in more exotic environments or processing by unknown mechanisms. The declination to apply decoy arguments to previous interstellar visitors deserves examination. Oumuamua's unusual characteristics certainly sparked speculation about artificial origins, but these discussions focused on the object's intrinsic properties rather than its potential role in masking other activities. Borisov appeared so conventionally cometary that artificial hypotheses received little serious consideration. 3I Atlas falls between these extremes, displaying enough anomalous characteristics to warrant investigation while maintaining plausible natural explanations. Statistical considerations about interstellar visitor populations continue evolving as detection capabilities improve. The Catalina Sky Survey, Linear, and other programs that discovered the first interstellar objects operated with limited sensitivity and sky coverage. The Atlas network that found 3I Atlas represents improved capabilities, while the upcoming Vera Rubin Observatory will revolutionize interstellar object detection through systematic, deep sky monitoring. As detection rates increase, the apparent rarity of interstellar visitors will diminish, potentially reducing the significance we attach to individual objects. If Rubin discovers dozens of interstellar visitors annually, 3I Atlas will represent one example among many, rather than a unique phenomenon demanding extraordinary explanations. This statistical dilution could strengthen natural interpretations while raising new questions about interstellar object populations. The visual comparative analysis reveals interesting patterns across all three visitors. Oumuamua approached from the direction of the constellation Lyra, passed close to the Sun, and departed toward Pegasus. Borisov arrived from Cassiopeia, displayed peak activity around perihelion, and continued toward Telescopium. 3I Atlas approaches from Sagittarius, will reach perihelion in late October, and should depart toward northern constellations if it survives solar heating. Perihelion distances vary significantly. Oumuamua passed within 0.25 astronomical units of the Sun, experiencing intense heating that might have driven its mysterious acceleration. Borisov reached approximately 2 astronomical units at closest approach, remaining cool enough to preserve volatile materials throughout its passage. 3I Atlas will approach to approximately 1.4 astronomical units, intermediate between its predecessors, and potentially revealing how moderate solar heating affects interstellar materials. Activity levels create another useful comparison metric. Oumuamua displayed no detectable coma despite close solar approach, suggesting either refractory composition or complete volatile depletion. Borisov showed strong activity beginning at large distances and continuing throughout its visible passage. 3I Atlas demonstrates moderate activity that began around 4 astronomical units from the Sun and should intensify as it approaches perihelion. Size estimates for all three objects remain somewhat uncertain due to albedo assumptions and distance effects. Oumuamua measured approximately 100 meters in its shortest dimension, with length potentially reaching several hundred meters. Borisov's nucleus probably measured around 1 kilometer in diameter. 3I Atlas appears similar to Borisov in overall scale, though precise dimensions await better observational constraints. The trajectory comparison reveals how detection bias affects the apparent distribution of interstellar visitor orbits. All three objects passed through the inner solar system during periods when Earth-based surveys could detect and track them effectively. Objects arriving at different times of year or following trajectories that avoid survey coverage areas would remain undiscovered, potentially skewing our understanding of typical interstellar visitor characteristics. The narrative of ordinary extraordinary emerges from considering these three objects collectively. Each represents an extraordinary event, materials formed around distant stars visiting our solar system, while displaying characteristics that may prove typical of broader interstellar populations. This perspective helps calibrate expectations and reduces the temptation to invoke exotic explanations for every unusual observation. The lesson for evaluating 3I Atlas lies in maintaining appropriate scientific skepticism while remaining open to genuine surprises. Oumuamua taught us that interstellar objects can display characteristics unlike anything in our solar system. Borisov demonstrated that some interstellar visitors behave exactly as natural processes predict. 3I Atlas may represent either category or something entirely new that expands our understanding once again. As we prepare for the critical observation period around 3I Atlas's perihelion, the comparison with its predecessors provides both context and caution. Each interstellar visitor has surprised astronomers in different ways, suggesting that our universe contains more variety than our theories anticipate. The question becomes whether 3I Atlas will surprise us with its ordinariness or its uniqueness. Part 10. UAP angle without hype. What would a real correlation look like? Science advances by testing hypotheses we'd rather not consider. Avi Loeb's suggestion to monitor unidentified aerial phenomena reports during 3I Atlas's perihelion passage represents precisely the kind of bold hypothesis that serious science should evaluate rather than dismiss. The logic follows straightforward reasoning. If 3I Atlas serves as a decoy to mask other activities in our solar system, those activities might produce detectable effects in Earth's atmosphere or near-space environment during the optimal observation window. The Galileo project, Loeb's scientific initiative dedicated to systematic UAP investigation, operates 3 observatory locations equipped with sophisticated sensor arrays designed to detect and characterize aerial phenomena through objective, reproducible measurements. These facilities provide exactly the kind of controlled monitoring capability needed to test correlations between interstellar visitor timing and unusual atmospheric observations. Establishing a rigorous test protocol requires careful attention to methodology that prevents false correlations and confirmation bias. The investigation must define specific geographic and temporal windows around 3I Atlas's closest approach, establish control periods when no correlation should exist, and prioritize sensor-based detections over anecdotal reports that introduce subjective interpretation and cultural contamination. The data source hierarchy proves crucial for maintaining scientific credibility. Galileo project sensor logs represent the highest quality evidence, calibrated instruments producing quantitative measurements under controlled conditions. Civil aviation radar data and space tracking systems provide secondary confirmation with known performance characteristics. Public reports, while potentially valuable for identifying investigation targets, carry substantial reliability concerns and require independent verification. Defining meaningful correlation versus background noise demands statistical sophistication. Earth's atmosphere regularly produces phenomena that untrained observers might interpret as anomalous. Meteor events, satellite re-entries, atmospheric plasma formations, military aircraft operations, and various optical illusions created by atmospheric conditions. Any perceived spike in UAP reports must exceed these baseline rates by statistically significant margins. The solar conjunction observation gap creates particular challenges for correlation studies. As 3I Atlas passes behind the Sun from Earth's perspective, ground-based monitoring becomes impossible, creating a natural blind period when hypothetical related activities might occur undetected. Testing requires comparing activity levels before, during, and after conjunction to identify patterns that might support or refute correlation hypotheses. Confounding factors require systematic consideration and filtering. October meteor showers, including the Orionids, occur during 3I Atlas's perihelion period and could produce numerous bright atmospheric events that generate UAP reports. Satellite constellation deployments, particularly large-scale launches of communication satellites, create formations that appear unusual to casual observers. Solar activity affects atmospheric conditions and radio propagation in ways that might influence both natural phenomena and detection systems. If genuine correlation emerges from this analysis, the investigation must prepare for rapid follow-up observations. Triangulation capabilities across multiple Galileo project sites could determine altitudes, velocities, and flight patterns of detected objects. Spectroscopic analysis might reveal emission signatures that distinguish between natural atmospheric phenomena, technological objects, and unknown categories. Multi-site confirmation prevents localized effects or instrumental artifacts from generating false positive results. Conversely, if no correlation appears despite careful monitoring, the decoy hypothesis loses significant supporting evidence. The absence of increased UAP activity during optimal masking periods would suggest either that 3I Atlas represents a natural object with no associated technologies, or that any hypothetical advanced activities produce no detectable atmospheric signatures. Communication ethics become particularly important when investigating UAP correlations. The scientific community must separate rigorous hypothesis testing from conspiratorial narratives that assume conclusions without supporting evidence. Clear communication about methodology, uncertainty levels, and negative results prevents public misunderstanding while maintaining scientific credibility. The investigation design should include pre-registered analysis criteria to prevent data mining and confirmation bias, establishing clear methodological standards that distinguish genuine scientific inquiry from motivated reasoning. Researchers must specify in advance what constitutes significant correlation, how they will handle multiple comparisons problems that arise when testing numerous potential relationships simultaneously, and what negative results would falsify the correlation hypothesis definitively. Such pre-registration ensures that post-hoc explanations don't contaminate objective analysis by preventing researchers from adjusting their criteria after seeing the data. The scientific community has learned from decades of false positive results in various fields that proper experimental design requires committing to specific hypotheses and analysis methods before data collection begins. The multiple comparisons problem becomes particularly acute when searching for correlations between astronomical events and terrestrial phenomena. If researchers test dozens of different time windows, geographic regions, detection methods, and correlation metrics, purely random chance will eventually produce apparently significant results that don't reflect genuine physical relationships. Proper statistical correction methods must account for all comparisons performed, not just the ones that appear in final publications. Privacy considerations constrain some aspects of UAP correlation studies in ways that balance scientific transparency with legitimate security and privacy concerns. Detailed flight tracking data from civil aviation systems contain information about specific aircraft operations that airlines and regulatory agencies may not wish to disclose publicly. Military radar observations often involve classified sensor capabilities and operational procedures that cannot be shared with civilian researchers. Civilian air traffic control information may require security clearances or institutional agreements that limit public access, creating challenges for independent verification of claimed correlations. The balance between scientific transparency and legitimate privacy concerns requires careful attention to data sharing protocols that enable meaningful analysis while protecting sensitive information. Personal privacy issues arise when UAP reports include specific witness information, location details, or circumstances that could identify individual observers. While such information may prove scientifically valuable for assessing report credibility and ruling out conventional explanations, ethical research practices require protecting witness privacy and avoiding potential harassment or ridicule from public disclosure. The broader scientific value of rigorous UAP correlation studies extends beyond 3i Atlas, specifically to developing general methodologies for testing connections between astronomical events and terrestrial phenomena. Solar flare effects on technology systems, meteor shower impacts on atmospheric chemistry, gravitational wave event correlations with terrestrial systems, and other potential relationships could benefit from the methodological frameworks developed for this investigation. Establishing standard protocols for investigating such correlations would advance multiple fields of research while preventing the methodological inconsistencies that have plagued some previous attempts to identify astronomical terrestrial connections. Clear guidelines for data collection, statistical analysis, and result interpretation would help distinguish genuine discoveries from artifacts of poor methodology. Quality control measures must distinguish between instrumental artifacts, atmospheric phenomena, and genuinely anomalous observations through systematic verification procedures that eliminate false positive results. Calibration procedures ensure that sensors respond predictably to known inputs across their full operating ranges. Background subtraction techniques remove systematic effects that could mimic genuine signals. Cross-validation with independent instrument systems confirms that observations represent real physical events rather than measurement anomalies. The challenge of separating signal from noise becomes particularly acute when searching for subtle effects that might be masked by much stronger conventional phenomena. Advanced data analysis techniques, including machine learning approaches and sophisticated filtering algorithms, may be necessary to identify weak correlations that conventional statistical methods cannot detect reliably. Systematic error analysis requires understanding all potential sources of bias or artifact that could produce false correlations. Seasonal variations in atmospheric conditions, changes in observer behavior patterns, modifications to sensor systems or analysis procedures, and numerous other factors could create apparent correlations that don't reflect genuine physical relationships. The geographic distribution of Galileo project observatories provides limited but useful spatial coverage for correlation studies, though expanding this network would improve the statistical power and geographic generalizability of any discovered relationships. Comparing detection rates across different locations tests whether any observed phenomena represent localized atmospheric effects, regional bias in reporting patterns, or broader phenomena that might support more exotic explanations. International collaboration could significantly enhance the geographic coverage and data quality available for correlation studies. Existing UAP research programs in various countries could contribute observational data and analysis capabilities that exceed what any single institution could achieve independently. However, such collaboration requires careful attention to data quality standards and methodological consistency across different research groups. Temporal resolution requirements depend on the specific correlation hypothesis being tested, with different physical mechanisms suggesting different characteristic timescales for any relationships between 3i Atlas and terrestrial phenomena. If the interstellar visitor serves as temporary camouflage for other activities, the effect might manifest over hours or days around perihelion. If it represents longer-term strategic positioning, correlations might extend across weeks or months of observation. High-frequency monitoring capabilities could detect rapid variations that might be missed by less frequent sampling, but they also increase data volume and analysis complexity while potentially introducing additional noise sources. The optimal observing strategy balances temporal resolution against signal-to-noise considerations and available computational resources for data processing. The investigation must also consider whether any detected correlations might result from increased observer attention rather than increased phenomena frequency. Media coverage of Three-Eye Atlas could prompt more people to watch the sky carefully, leading to higher reporting rates of ordinary phenomena that would normally pass unnoticed. This observational bias effect could create apparent correlations that reflect human behavior changes rather than genuine physical relationships. Control group analysis becomes essential for distinguishing between genuine correlations and observation bias effects. Comparing UAP report rates during Three-Eye Atlas coverage with rates during coverage of other astronomical events could reveal whether apparent correlations reflect specific physical relationships or general effects of increased sky watching behavior. The baseline UAP detection rate varies significantly with location, season, weather conditions, cultural factors, and numerous other variables that complicate correlation analysis. Understanding these background variations requires extensive historical data analysis that establishes normal detection patterns against which any Three-Eye Atlas-related changes can be evaluated. Seasonal effects deserve particular attention because Three-Eye Atlas reaches perihelion during autumn in the Northern Hemisphere, when atmospheric conditions, daylight patterns, and observer behavior differ systematically from other times of year. Any apparent correlation could reflect these seasonal factors rather than specific relationships with the interstellar visitor. Weather pattern influences on both atmospheric phenomena and UAP detection rates create additional confounding factors that must be considered in correlation analysis. Clear skies increase visibility for both conventional and potentially anomalous phenomena, while weather fronts and atmospheric instability can create optical effects that might be misinterpreted as unusual aerial objects. As Three-Eye Atlas approaches its critical perihelion period, the UAP correlation study represents exactly the kind of scientific investigation that advances knowledge regardless of outcome. Either result, correlation or its absence, constrains possible explanations and improves our understanding of both interstellar visitors and atmospheric phenomena, while demonstrating rigorous methodologies for testing extraordinary hypotheses through systematic observation. The beauty of rigorous hypothesis testing lies not in confirming preconceptions, but in letting reality surprise us with truth more interesting than speculation. Whether that truth supports conventional explanations or reveals phenomena that challenge our current understanding of how the universe operates. The broader scientific value of this investigation extends beyond Three-Eye Atlas specifically. Developing rigorous methodologies for testing correlations between astronomical events and atmospheric phenomena advances capabilities for investigating other potential connections, solar flare effects on technology, meteor shower impacts on atmospheric chemistry, or gravitational wave event correlations with terrestrial systems. Quality control measures must distinguish between instrumental artifacts, atmospheric phenomena, and genuinely anomalous observations. Calibration procedures, background subtraction techniques, and systematic error analysis prevent false signals from contaminating datasets. Cross-validation with independent instrument systems confirms that observations represent real physical events rather than measurement anomalies. The geographic distribution of Galileo project observatories provides limited but useful spatial coverage for correlation studies. Comparing detection rates across different locations tests whether any observed phenomena represent localized atmospheric effects or broader patterns that might support more exotic explanations. Temporal resolution requirements depend on the specific correlation hypothesis being tested. If Three-Eye Atlas serves as temporary camouflage for other activities, the effect might last hours or days around perihelion. If it represents long-term strategic positioning, correlations might extend across weeks or months. Different timescales require different analysis approaches and statistical techniques. The investigation must also consider whether any detected correlations might result from increased observer attention rather than increased phenomena. Media coverage of 3I Atlas could prompt more people to watch the sky carefully, leading to higher reporting rates of ordinary phenomena that would normally pass unnoticed. Distinguishing between observational bias and genuine correlation requires careful control group analysis. As 3I Atlas approaches its critical perihelion period, the UAP correlation study represents exactly the kind of scientific investigation that advances knowledge regardless of outcome. Either result, correlation or its absence, constrains possible explanations and improves our understanding of both interstellar visitors and atmospheric phenomena. The beauty of rigorous hypothesis testing lies not in confirming preconceptions, but in letting reality surprise us with truth more interesting than speculation. Part 11. Media, public imagination, and scientific process. Truth travels slower than headlines, but it arrives with better documentation. The media coverage of 3I Atlas illustrates both the power and peril of science communication in an era where astronomical discoveries compete for attention with countless other information streams. Early headlines proclaimed it the largest, brightest, or fastest interstellar visitor, creating public expectations that subsequent analysis would necessarily revise downward as measurement precision improved. NASA's official communications emphasized safety and evidence-based interpretation from the beginning. Their press releases consistently stated that 3I Atlas posed no threat to Earth, remained at safe distances throughout its solar system passage, and displayed characteristics consistent with natural cometary activity. This measured approach balanced public interest with scientific responsibility, avoiding both sensationalism and premature dismissal of interesting observations. Popular science outlets like Space.com, EarthSky, and major newspapers including The Guardian approached the story from various angles. Some emphasized the rarity and excitement of interstellar visitor discoveries. Others focused on potential connections to previous objects like Oumuamua. A few highlighted the more speculative interpretations proposed by researchers like A.V. Loeb, sometimes without adequate context about scientific consensus. Loeb's prolific public writing through Medium posts and interviews presents both advantages and challenges for science communication. His willingness to discuss bold hypotheses before peer review completion accelerates public engagement with cutting-edge research. However, it also risks creating false impressions about scientific consensus when preliminary speculations receive equal media attention with established findings. The danger of premature certainty affects public understanding in complex ways. When early estimates suggest 3I Atlas might be the largest interstellar object, subsequent revisions toward more modest sizes can appear to diminish the discovery's significance rather than representing normal refinement of scientific understanding. The public expects science to provide definitive answers quickly, while the scientific process requires patience and iterative improvement. Peer review serves as crucial quality control that balances bold hypotheses against rigorous evidence standards. The Hubble Space Telescope paper by David Jewett's team underwent multiple revisions as new observations became available, demonstrating how scientific understanding develops through careful analysis rather than instant revelation. Each version improved measurement precision while maintaining core conclusions about natural cometary activity. Social media platforms and specialized forums like Space Exploration Stack Exchange provide venues where mission proposals receive rapid community evaluation. The Juno retargeting idea generated extensive technical discussion about propulsion requirements, mission feasibility, and scientific priorities. Such public discourse can identify practical constraints and alternative approaches that formal review processes might miss. The challenge for science communicators lies in conveying the excitement of discovery while maintaining appropriate uncertainty about preliminary findings. 3I Atlas represents a genuinely significant astronomical event, regardless of whether it proves natural or artificial. The process of investigation advances our capabilities for detecting and characterizing interstellar objects, even if specific hypotheses prove incorrect. Visual representation plays crucial roles in public understanding of scientific concepts. Hubble images of 3I Atlas's teardrop coma provide intuitive understanding of the object's activity that numerical data alone cannot convey. However, image processing choices, color enhancement, contrast adjustment, orientation selection can influence public perception of what the observations actually reveal. Editorial standards for documentary productions require particular attention to accuracy and context. Scientific speculation must be clearly labeled as hypothesis rather than established fact. Consensus interpretations deserve appropriate weight relative to minority viewpoints. On-screen citations should direct audiences to primary sources rather than secondary reporting that might introduce distortions. The use of color coding or other visual grammar can help audiences distinguish between established observations, mainstream interpretations, and speculative hypotheses. Such techniques prevent confusion about the evidential status of different claims while maintaining narrative flow that keeps viewers engaged throughout complex scientific discussions. The historical perspective from Oumuamua coverage provides valuable lessons for avoiding mystery inflation, the tendency to emphasize unexplained aspects while downplaying successful explanations. Oumuamua's unusual characteristics generated extensive media coverage of artificial origin hypotheses, but less attention to subsequent research that identified plausible natural mechanisms for its behavior. Documentary production must balance dramatic storytelling with scientific responsibility. Focusing on tests and methodology rather than unsupported speculation maintains audience interest while advancing scientific literacy. The most compelling story often lies in the process of investigation, rather than predetermined conclusions about mysterious phenomena. Real-time science communication faces unique challenges when dealing with fast-evolving discoveries. 3I Atlas observations continue generating new data that could revise interpretations significantly before the documentary reaches audiences. Acknowledging this temporal uncertainty while providing current best understanding requires careful scripting that remains accurate despite inevitable future developments. The global nature of astronomical research creates opportunities for international perspectives on scientific discoveries. 3I Atlas receives attention from observatories, researchers, and media outlets worldwide, potentially revealing cultural differences in how different societies interpret unusual phenomena or evaluate extraordinary claims. Educational impact extends beyond immediate entertainment value to long-term scientific literacy effects. Audiences who understand how astronomers test hypotheses about 3I Atlas gain tools for evaluating future discoveries and distinguishing between credible research and pseudo-scientific speculation. The methodology lessons prove more valuable than specific conclusions about individual objects. The relationship between public excitement and research funding creates additional communication considerations. High-profile discoveries like interstellar visitors can generate political and financial support for astronomical research, but only if public understanding aligns reasonably well with scientific reality. Overselling preliminary findings risks backlash when expectations exceed actual discoveries. Professional responsibility requires scientists and science communicators to consider long-term credibility alongside short-term impact. Sensational claims that later prove unfounded can damage public trust in scientific institutions and make audiences skeptical of future legitimate discoveries. The most responsible approach emphasizes what we know, what we don't know, and how we plan to learn more. As 3I Atlas approaches perihelion and generates continued observations, the media coverage will likely evolve from discovery announcements through detailed analysis toward final interpretation of what this visitor teaches us about interstellar objects. Each phase requires different communication strategies that match audience expectations with scientific capabilities. The ultimate test of successful science communication lies not in generating maximum attention, but in advancing public understanding of how science works and why evidence-based reasoning produces more reliable knowledge than speculation or wishful thinking. Part 12. Verdict Paths. A decision tree from data to conclusion. Every mystery eventually chooses its own ending through the weight of accumulated evidence. As 3I Atlas approaches the critical observation period around its October 30th perihelion, the accumulated data will guide us down one of several distinct paths toward understanding what this cosmic visitor truly represents. The decision tree ahead branches according to observational evidence rather than preconceived notions, offering multiple scenarios that range from conventional cometary physics to paradigm-shifting discoveries. Path A represents the most probable outcome based on current evidence. Standard comet physics confirmed through comprehensive observations. In this scenario, spectroscopic analysis reveals gas emission lines consistent with water vapor, carbon monoxide, and other species typical of comets formed in outer planetary regions. Comet brightness profiles match mathematical models of dust particles scattering sunlight as they move away from the nucleus under radiation pressure. Tail development follows predictable patterns of ion and dust emission driven by solar heating and radiation pressure effects. The nucleus size measurements in Path A would confirm kilometer-scale dimensions consistent with natural gravitational accumulation of materials in protoplanetary disks. Mass loss rates would evolve according to established relationships between solar heating, surface area, and volatile sublimation temperatures. The object's rotation period and brightness variations would reflect irregular shape and surface markings typical of small solar system bodies modified by impact cratering and thermal processing. Path B leads toward persistent anomalies that resist conventional explanation despite thorough investigation. Here, high-cadence photometry might reveal brightness variations inconsistent with reflected sunlight, suggesting internal illumination sources that exceed reasonable estimates for natural heating mechanisms. Spectroscopic observations could detect emission lines at wavelengths that don't correspond to known molecular transitions, indicating exotic chemistry or artificial light sources. Thermal infrared observations in Path B might show temperature distributions incompatible with pure solar heating, particularly if hot regions appear on the object's night side or display geometric patterns suggesting technological heat sources. Polarization measurements could reveal coherent light characteristics inconsistent with dust scattering, potentially indicating artificially generated illumination. Path C encompasses mixed evidence scenarios where some observations support natural interpretation, while others suggest anomalous characteristics. This intermediate path might reveal nucleus sizes at the smaller end of natural ranges while displaying activity levels higher than expected for such dimensions. Chemical composition might prove unusual but not impossible for natural formation processes. Structural features might appear geometric but remain plausibly explained by natural fracturing or impact processes. The conclusive tests for distinguishing among these paths require sophisticated observational campaigns across multiple wavelengths and temporal baselines. Spectroscopy bands in the infrared and visible wavelengths can identify specific molecular species and their abundances, revealing whether 3I Atlas contains materials consistent with cometary formation or exotic compositions suggesting different origins. High-cadence photometry with precision approaching 1% can detect subtle brightness modulations that might indicate artificial signals or reveal natural processes like outburst events driven by subsurface volatile pockets. Polarization measurements distinguish between reflected sunlight and thermal emission, while potentially identifying coherent light sources inconsistent with natural scattering processes. Radar observations, if geometrically feasible from facilities like Arecibo or Goldstone, could determine surface properties, rotation characteristics, and internal structure through echo timing and polarization analysis. Such measurements would reveal whether 3I Atlas displays solid, coherent structure typical of rocky bodies or loose aggregate properties expected for naturally formed comets. The timeline for these decisive observations follows 3I Atlas's orbital geometry through several critical periods. Perihelion around October 30th offers maximum solar heating and peak activity levels when any unusual characteristics should become most apparent. Solar conjunction creates a natural observation gap from November through early December when Earth-based monitoring becomes impossible. The early December reappearance provides opportunities to assess how 3I Atlas survived its close solar encounter. Natural comets often display dramatic changes in activity levels, coma structure, or even complete disintegration following perihelion passage. Artificial objects might display different responses to intense solar heating and radiation environment. The potential March 2026 geometry near Jupiter offers additional observation opportunities if 3I Atlas remains intact and detectable. By this time, accumulated observations should provide sufficient data to distinguish definitively among the competing interpretation paths. Null results play equally important roles in this decision process. If spectroscopic observations fail to detect expected cometary gas species, if thermal measurements reveal no internal heat sources, if polarization studies show only reflected sunlight, each negative finding constrains possible explanations and reduces the probability space available for exotic interpretations. The statistical framework for evaluating these paths requires Bayesian updating as new evidence accumulates. Prior probabilities based on the rarity of artificial objects versus the abundance of natural comets shift systematically as observations either support or contradict specific predictions. The extraordinary evidence threshold for extraordinary claims means that Path B requires overwhelming observational support to overcome strong natural priors. When to retire the decoy hypothesis versus keeping it alive depends critically on the accumulation of evidence that definitively favors natural explanations. If Path A evidence emerges consistently across multiple independent observation campaigns, scientific conservatism suggests accepting the conventional interpretation while remaining alert for future objects that might display genuinely anomalous characteristics. Policy recommendations flowing from this investigation extend beyond 3I Atlas to broader preparedness for future interstellar visitors. Regardless of which path proves correct, the experience demonstrates critical needs for rapid response capabilities that can deploy sophisticated instrumentation to study unexpected targets within tight temporal windows. Dedicated interstellar interceptor missions deserve serious consideration for future space program priorities. Unlike retrofitting existing spacecraft for unplanned encounters, purpose-built interceptors could carry optimized instrument suites and maintain readiness for rapid deployment toward high-priority targets. Solar sail propulsion or advanced ion engines might provide the continuous acceleration needed to match velocities with fast-moving interstellar objects. Rapid tasking protocols for existing space telescopes require development and testing before the next interstellar visitor arrives. Coordinating observations across Hubble, James Webb, and ground-based facilities demands advanced planning that current astronomical scheduling processes don't accommodate well. Emergency observation procedures could ensure optimal data collection during critical periods. International cooperation frameworks prove essential for maximizing scientific return from rare astronomical events. 3I Atlas observations benefit from contributions by observatories, space agencies, and research institutions worldwide. Formalizing such cooperation through advance agreements could improve coordination and data sharing for future discoveries. Contingency planning for persistent anomalies must address how the scientific community would respond if Path B evidence emerges convincingly. Independent reanalysis by multiple research teams would be essential for confirming extraordinary results and eliminating systematic errors or biases. Open data releases would enable broad community participation in verification efforts. Non-optical sensors deserve consideration for comprehensive anomaly investigation. Radio telescopes might detect artificial signals or unusual electromagnetic emissions. X-ray observatories could identify high-energy processes inconsistent with natural cometary activity. Gravitational wave detectors, while unlikely to detect signals from objects as small as 3I Atlas, illustrate the principle of using multiple physical phenomena to characterize unusual objects. Public-facing communications require different approaches for each outcome path. Path A results should emphasize the scientific value of confirming natural processes while advancing our understanding of interstellar materials and cometary physics. Path B findings would demand extraordinary care in presenting evidence while avoiding sensationalism or premature conclusions. Path C scenarios require nuanced communication about scientific uncertainty and the iterative nature of hypothesis refinement. The comparative framework with previous interstellar visitors provides essential context for interpreting 3I Atlas results. Since 2017, our capabilities for detecting and characterizing such objects have improved dramatically through better instruments, more sophisticated analysis techniques, and accumulated experience with unusual astronomical phenomena. Progress since Oumuamua and Borisov includes enhanced spectroscopic capabilities from James Webb Space Telescope, improved imaging resolution from upgraded ground-based adaptive optics systems, and better theoretical understanding of how interstellar objects should behave under various physical conditions. Each advancement increases our ability to distinguish between natural and artificial characteristics. 3I Atlas advances the field regardless of which interpretation path proves correct. If natural, it provides unprecedented insights into materials formed around distant stars and how they evolve during interstellar journeys spanning millions of years. If artificial, it represents the first confirmed detection of extraterrestrial technology, fundamentally changing our understanding of intelligence in the universe. The investigation methodology developed for 3I Atlas creates templates for evaluating future anomalous objects. The systematic approach to hypothesis testing, evidence evaluation, and conclusion formation serves as a model for maintaining scientific rigor while remaining open to paradigm-shifting discoveries. Ethical considerations require keeping extraordinary claims provisional until extraordinary evidence reaches compelling levels. The scientific community bears responsibility for honest communication about uncertainty, alternative explanations, and the limitations of current observations. Premature certainty in either direction, natural or artificial, deserves both science and public understanding. Educational value emerges from documenting the complete investigative process, including wrong turns, failed hypotheses, and methods that proved more or less effective than anticipated. Students and future researchers benefit from understanding how real science works rather than sanitized versions that omit uncertainty and revision. The timeline pressure created by 3I Atlas's rapid passage through our solar system illustrates broader challenges in astronomical research. Unlike laboratory experiments that can be repeated indefinitely, astronomical phenomena often provide single opportunities for data collection. This constraint demands maximum efficiency in observation planning and execution. Looking toward the future, the Vera Rubin Observatory will discover numerous additional interstellar objects, potentially dozens annually once fully operational. This abundance will provide statistical samples large enough to evaluate population characteristics and identify genuinely unusual objects against a background of typical interstellar visitors. Machine learning applications to interstellar object characterization could accelerate the identification of anomalous characteristics by comparing new observations against databases of natural object properties. Automated alert systems might flag objects displaying unusual brightness variations, spectroscopic features, or trajectory characteristics for priority follow-up observation. The closing image returns us to where this investigation began. The same Hubble Space Telescope frame that first revealed 3I Atlas's teardrop coma, now annotated with everything we've learned about what to watch for in the critical observations ahead. The dust plume that initially suggested simple cometary activity might represent exactly that, or it might camouflage something far more extraordinary. As 3I Atlas approaches its moment of closest solar encounter, carrying secrets that formed around distant stars, We prepare for answers that will either confirm our understanding of how the universe works, or challenge us to expand that understanding in ways we never anticipated. The verdict awaits not in speculation or wishful thinking, but in the objective measurement of photons that have traveled across interstellar space to reach our instruments during this brief window of cosmic opportunity. Whether 3I Atlas proves to be the most ordinary extraordinary object we've ever studied, or the most extraordinary ordinary-looking visitor we've ever encountered, depends entirely on what those photons choose to reveal in the darkness between worlds. The universe keeps its own counsel, but sometimes, if we listen carefully enough with sensitive enough instruments, it whispers its secrets to those patient enough to hear them.